So, let us continue with nuclear and particle physics. So, we have been discussing about beta decay. Now, we shall discuss gamma decay and more details of gamma decay. So, we shall outline nuclear isomerism, internal conversion and nuclear reactions. So, when you say isomerism, it is the same nucleus having two different lifetimes of decay. So, isomers have same A and Z, but different lifetimes of decay, which means it is the same nucleus species, same species, but exhibiting two different lifetimes. See, for example, if you take cobalt 60, it is a beta minus emitter and it emits with one half life. All the nuclei will be species, all the nuclei will be emitted with same half life. But there are some nuclei elements or isotopes which exhibit two different lifetimes. For example, bromine, it has got two different lifetimes. So, a nucleus, a nuclide, if it is having two different decay times, then it is called an isomer. So, here we have written that isomers have same A and Z, but different lifetimes of decay. So, TF is different because of different energy levels. So, we have got two different energy levels. See, normally we will have ground state, excited state. If there is only ground state and excited state, then the energy difference will be same, half life will be same. Suppose I got excited state, metastable state and ground state. In that case, we will have a transition from excited to ground, the metastable to ground. Therefore, we will have two different lifetimes. So, a nucleus, if it is having a metastable state also, then we will have two different half lives of decay. So, we have got many elements, but we are considering bromine. Bromine, natural bromine has got two isotopes, 79 and also Br 81. Now, suppose neutron is bombarded on this bromine, some of the neutrons will be bombarding 79 and some will be bombarding 81, which means both bromine 79 and bromine 81 are exposed to neutron if you are sending neutron beam. So, in that case we will just see what will happen. So, when the 79 is bombarded with neutron, we get bromine 80 because 79 plus 1 80. Now, this bromine 80 is an isomer. Isomer, say just before going further, you just remember the word, the letter M. M refers to, for us to remember, I am telling, M refers to the metastable state. So, when there is a metastable state, it will have two different lifetimes. Even if you go through the Clark's table, all the elements, some elements will be written as M, superscript M. It means it has got a metastable state and it will exhibit two different lifetimes. Now, this bromine has got two different lifetimes. So, we will just see what are the lifetimes. So, bromine, it is an isomer, it will emit beta minus particle and it becomes krypton 3680. Say this 35, atomic number 35 has become atomic number 36, which means it is a beta minus emission. So, beta minus particle comes out and therefore, the atomic number increases 35 to 36 it has become. The mass number remains the same. So, it is a typical beta minus emission. So, we have got two beta minus particles of two different lifetimes emerge out, with one of them T1 18 minutes, the other one is 4.5 hours. So, we have got two different lifetimes of decay. So, this bromine. Now, I will just go back to this one. This 81, that is also bombarded with the neutron, that will become 82. But the bromine 82 is not an isomer. So, it will have one lifetime. Therefore, before we go to the next point, we can just say if natural bromine is bombarded with the neutron, it will have this 80 giving two isomers, and this one it becomes 82, it has got one half life, this has got two half lives, this has got one half life. Therefore, as a result we will have natural bromine, it will give out beta particles with 3 half lives. So, that is what we go see in the next one. See, it has got excited state, ground state, metastable state and excited state. And when it is coming from excited to the lower, that is we called as T1. The other one from excited, it is going to metastable with gamma emission. It will go by gamma emission, and from this metastable state it will go to ground state. Now here as you see, this one is T1 and T2. Which do you think will be larger? See here, the energy difference is large. For T1, the energy difference is large, so it will come out with shorter half-life. You understand? So if you have got a energy difference is larger, it will come out with a shorter half-life. If the energy difference is small, it will come out with a larger lifetime. So for you to remember, you can just say, if you take a rubber band, pull it to a larger extent, it will come out faster. So if you extend to a smaller if you pull it to a smaller extent, it will come out slow. So here, which will be faster? This will be faster. T1 will be faster. So T1 will be faster, means short half-life. That's what we I will go to the previous one. T1 see is 18 minutes faster, and T2 is 4.5 hours. And so this the other one, bromine 81, if you bombard with a neutron, it becomes 82, and that 82 emits beta minus particle, bring out krypton, and it has got 6.4 minutes half-life. Therefore, when natural bromine is bombarded, we get 3 half-lives, namely natural bromine when it is bombarded by neutrons, we get 3 half-lives, namely 6.4 minute, for that is for the latter case we saw, and 18 minutes and 4.5 hours are due to the isomeric transitions. So altogether we get 3 half-lives. So the bromine is marked as BrM, superscript M. So in as we said in the table, if you see, wherever it is marked M, it means it is a isomer, it has got a metastable state in it. Now we said about beta decay with 2-3 different half-lives. Now if you take potassium 19, atomic number 19, mass number 41, if you take potassium isomer with 2 gamma emission, it comes out with 2 gamma emission. This bromine with the 3 beta half-lives, this one potassium gives gamma emission. Now when you talk about the gamma emission, when how do you get this isomeric state? If delta J is large, probability of decay is small. So there what we get is, we got an parent level, the energy level, and for example potassium has got one energy level, and then the other one metastable and ground state we get. Between the excited state and ground state, delta J is small, namely delta J equal to 1. So it comes out fast without any hindrance. If you take metastable and the ground state, the delta J is large. What is delta J? That is the spin of that level and spin of the other level, ground level. So when the spin is large, it will take a longer time. The probability of decay is small. When the probability of decay is small, it will take a longer time, half-life will be larger. We are not showing a diagram, but here again from excited to ground, from metastable to ground, we get 2 gamma emission. Now we will go to the other concept in gamma decay, internal conversion. So when gamma emission is prohibited, that energy is transferred to atomic electrons. Say what we have is, we have got excited nucleus, the nucleus is excited, it will de-excite by gamma emission, it will go to another level, gamma emission. But sometimes gamma will be prohibited, it has got highly excited energy, it is not able to come out. We will see what prohibits, we will just see what will be the prohibition. So when it is not allowed, when it is forbidden, when it is not allowed to come out, that energy will be given to atomic electron. Which is the closest electron? It is the K shell. In the atomic level, you have got K electron, L electron. So that will be transferred, the energy will be transferred to that one. Thereby the nucleus de-excites, comes to ground state. Now here energy of the excited state is W star. Then the energy of the ground state is W. Now what is the difference between the two nucleus de-excites? it is W star minus W will be the energy. This energy should come out as gamma. When the gamma is prohibited, it will be given to electron. So, what is the energy of the gamma? E will be W star minus W, that will be the energy. Now, when it is prohibited, the electron takes that energy. So, here we have got the energy can be given to K electron, L electron, M electron, but naturally K is very close to the nucleus. Therefore, we see that K electron conversion has got large probability. Then when you go to gamma decay and internal conversions, both are competing processes. So, when gamma emission will be there, when gamma is prohibited, we get the internal conversion taking place. So, in the case of internal conversion, what will be the kinetic energy of the electron? That will be W star minus W, and not only that, we have got minus W written there, because this electron is bound to the atomic shell. So, it requires some energy to be removed out, binding energy. So, first it has to be having the binding energy has to be removed, then we get this. Therefore, the kinetic energy will be this minus this. So, now here this WE is the binding energy of the electron in the atomic level. Now, here one difference will be the beta decay. Already we have discussed in beta decay, the curve is continuous. Beta decay spectrum is a continuous spectrum. That is because of the neutrino, all that we have discussed. So, because of the neutrino is sharing the energy, the beta spectrum is continuous, experimental spectrum. Whereas the conversion electron, those are also electrons which coming from the nucleus. See, when you say beta particle, that is also an electron which comes out from the nucleus, and this conversion electron, that is also coming from within the atomic level. This is coming from the atomic level. It is an electron coming from within the nucleus. This is from the atomic level. Now, here this will have line spectra. Therefore, when you do that beta decay experimental analysis, here we get number of beta particles in the y axis, and here this will be the energy. You will find that the beta particle will have the continuous curve this way, whereas the conversion electrons, K conversion, L conversion, they will be line spectrum. Now, here as we said, it is a competing process we said. So, internal conversion we just call it as coefficient, that coefficient alpha we just put. So, there will be n is the number of electrons which are internal conversion electrons which are emitted, and n gamma is the number of gamma. Therefore, this coefficient, this will be a small quantity, this will be a larger quantity. So, that Ne by n gamma we call it as internal conversion coefficient. Suppose there is no internal conversion electrons at all, for that particular system or nucleus we will have alpha equal to 0. About the decay constant, when you say decay constant lambda, it is probability of decay per second. Now, here we have got this probability of decay, total probability, this lambda represents total probability of decay per second, and the total probability will be equal to sum of gamma probability and electron probability, that is all, because it can either emit gamma or it can emit internal conversion electrons. Now, here already we said about prohibited, gamma is prohibited, when it is prohibited. So, gamma is a boson, so it is a spin 1 particle. So, we call it boson because it obeys Bose-Einstein statistics. So, it is a boson. Therefore, it has got spin s equal to 1, and delta j must be equal to 1. The delta j is between the nuclear spin of the excited state and the lower state, that must be equal to 1. Suppose if it is not equal to 1, if it is only 0, in that case it is prohibited. So, if delta j is equal to 0, gamma emission is prohibited, because gamma requires at least delta j equal to 1, that is a minimum condition. If delta j equal to 0, gamma emission is prohibited and internal conversion will take place, that is it. Therefore, it depends on this delta j value. Now, we will just go to nuclear reactions. See, we know about the chemical reaction. In a chemical reaction, electrons are involved. So, the nucleus will not be disturbed at all in a chemical reaction. Only the electrons will get transferred from one to this, change, covalent bond, all that. So, we get molecular formation, atom becomes a molecule, all that. The nucleus is not disturbed. Whereas, when you take nuclear reaction, it involves neutron and proton. Chemical reaction involves electron, nuclear reaction involves neutron and proton. So, when it involves neutron and proton, we get what is called nuclear transmutation. A nucleus changes, maybe carbon becomes nitrogen or nitrogen becomes oxygen. So, there is a change of nucleus, therefore, we call it as nuclear transmutation. Now, what are the types of reactions we have? See, here we have put small x, that is the incident particle. For example, it can be a neutron, proton or alpha particle, some incident particle you are just sending, and this is the target nucleus. For example, uranium or thorium is a target nucleus. So, when this is bombarded on this, what are the possibilities? I can get x plus x, which means nothing has happened. X plus x is equal to x plus x. This is called elastic scattering. So, there is no loss of energy, it is called elastic scattering. Suppose in this reaction the target is excited due to the incident particle, the target gets excited. So, we just put a star to show that it is excited. Here outgoing particle is same. So, the nucleus has not changed, it is only excited and therefore, it will de-excite by gamma radiation. So, the same nucleus only. Therefore, this is called inelastic scattering. Inelastic because it has lost some energy, there is energy change. The other one is y plus y. So, what you are sending is x plus x, y plus y, which means the nucleus, the target nucleus was x. Now, the product nucleus is y, the nucleus has changed. The incident particle is x, outgoing particle is some other particle y. Now, it means a nuclear reaction has taken place. Now, for example, we have got nitrogen 714 and the incident particle is alpha, this is alpha, helium 24 alpha. So, when you do put this, what will happen is, this is 14 plus 4, 18, see, and then this is 7 plus 2, 9, which means this alpha particle has embedded, it got embedded into nitrogen 714 and we get F918, and this F919 in all nuclear text you can see it will be put as bracket, this one in a square bracket it will be put, which conventionally it is to indicate it is a compound nucleus, it is called compound nucleus. This plus this has become this. So, it is called a compound nucleus. Compound nucleus is generally not stable, it will be unstable after some time depending on the half life of decay of this. The F918 becomes, it emits one proton. So, it becomes Y17 and H11, that is proton. So, here it is 18 and this is 9. Okay. Now, this is the, what has happened here is target plus alpha. See, this is the alpha particle and this is the target. Target plus alpha has become CN, compound nucleus, it has become compound nucleus, and we get the product is Y17 and the outgoing particle is proton. So, in this reaction what has happened is, this nitrogen has become oxygen. So, there is a transmutation, the nucleus itself has changed. Now, the same thing we are writing in a different style. So, nitrogen, that 7 is dropped because nitrogen atomic number is, we know, 7. Similarly, oxygen atomic number 8 we know. So, that is dropped. So, in all journals the convention is we need not write the whole equation, but we can write as alpha p. What is this alpha and this is p? Alpha is the incident particle and p is the outgoing particle. So, nitrogen has become oxygen in this alpha p reaction. So, here go to the previous one. So, the incident particle is alpha, outgoing particle is proton. So, it is called alpha p reaction. So, this was first done by Rutherford. So, we are just mentioning. So, generally these reactions are called alpha p reaction. So, it can be nitrogen and oxygen. You can use some other target and we will see what you are getting here. You can use change the target. Therefore, generally we can write as alpha p reaction. Here we have got next reaction helium 24 plus beryllium 49. So, here this reaction will give carbon 612 and nitrogen. So, here this is say 9 plus 4 13, here 12 plus neutron has got mass number 1 13. See here this is 2 and 4 the atomic numbers, here is 6 and neutron has got 0. So, this equation is valid. Now, we have got this one incident particle is alpha, outgoing particle is neutron. So, we can write as beryllium alpha n carbon 12 reaction, or generally we can call it as alpha n reaction. So, this is a general term where the target can be different and the product nucleus will be different. Here this is alpha plus beryllium C12, and this particular reaction, why we are putting it, it was done by Chadwick, and this led to the discovery of neutron. So, he bombarded Chadwick bombarded beryllium with the alpha particle and he got carbon 612 which is a stable nucleus, and then neutron was emitted. So, this led to the discovery of neutron, that was done by Chadwick. Now, just another example of a reaction, lithium 37 plus proton will give you helium 24 plus 2 alpha particle, because alpha is a stable cluster, lithium is unstable, we get 2 alpha particle emitted. What are the conservation laws for the nuclear reactions? For all nuclear reaction, energy is conserved. So, that generally conservation of energy is valid everywhere. So, there must be energy must be conserved. In a reaction, energy is conserved. The left hand side energy must be equal to the right hand side energy. Then charge is also conserved. When you say charge is conserved, it means atomic number is conserved. So, take this reaction, neutron become proton and it emits beta minus particle and antineutrino. So, as far as charge is concerned, neutron has got the charge 0 and proton charge plus 1 and beta minus particle charge minus 1. Therefore, charge will be conserved and this is chargeless. So, the charge is, this is a valid reaction where neutron is converted to proton by beta minus emission, and here the charge is conserved. The mass number is also conserved. Mass number is total number of nucleons. So, the nucleon number is conserved, or that nucleon is also called baryon. So, the baryon number is conserved. All the neutron and proton are called baryons. That is also conserved. We will just go back to this reaction. So, here 1 baryon, here this 1 baryon. These are not baryons. Therefore, the baryon number left side 1, right side 1. So, the baryon number is also conserved. Then we have lepton number is conserved. So, when you say lepton, you remember letter L, light particles. Light particles are called leptons. So, the number of light particles will remain constant. So, lepton number is constant, and here all the light particles have lepton number L equal to 1, antiparticles have L equal to minus 1. Now, here when you say particle, electron is a particle, therefore, electron should have plus 1 and positron is antiparticle. So, positron should have is an antiparticle, so it should have L equal to minus 1. Neutrino is a particle and therefore, it should have plus 1. Antineutrino is antiparticle, so minus 1. So, keeping this in mind, we will go back to this one. So, here lepton number is constant. This is not a lepton. So, left side lepton number is 0. Here this is not a lepton. So, it is 0. Here we get a beta minus particle which has got lepton number plus 1, and this is antineutrino, it has got minus 1. So, plus 1 minus 1, lepton number cancels here, left side 0, right side here plus 1 and minus 1 0. linear momentum. So, the linear momentum will be same in the reaction, because even in classical mechanics we have got that linear momentum is should be constant. So, here the linear momentum remains constant of the initial system and the final system in a nuclear reaction. Similarly, angular momentum will be constant for the angular momentum for the initial and final system, and spin angular moment, spin will also be constant. So, when you say spin is constant, this is linear momentum, total angular momentum, spin angular momentum. So, here we just see the same reaction. For simplicity, we are just taking the same reaction. Neutron becomes proton, plus we get beta minus and antineutrino. The neutron has got spin off and proton has got spin off, and beta minus particle is also electron, that is an electron, that is also a spin off particle. Antineutrino is also a spin off particle, because all neutrino and antineutrino, according to neutrino hypothesis, we found that it is a spin off particle. So, it is all spin off particle. Now, here what we have is we get this is off. So, this will be, it can have plus or minus off, plus off minus off, plus or minus off. Therefore, we will get maybe this will have plus off minus off cancel, and then we get plus off. So, the parity the spin will be conserved in this. Now, here statistics will also be conserved in a reaction. When you involve spin off particle, they obey Fermi-Dirac statistics, and when the spin is 0 or 1 integral spin, then B statistics. So, left side if it is having spin off, it obeys Fermi-Dirac statistics. Right side is also off, so we get Fermi-Dirac statistics. In certain other reactions, suppose this is here, it is 1, the other side will also be 1. So, the statistics is also conserved. Parity, in all strong interaction parity is conserved, and in weak interaction it is violated. Already in the beta decay we have just seen parity is violated in weak interaction. So, here we will just go to summary. So, we have discussed angular nuclear isomerism with the bromine as an example with an energy level diagram. So, we have discussed the conditions for internal conversion. So, when the gamma is prohibited, we get internal conversion, and we have just outlined a few reactions, and we have also enlisted the conservation laws. So, we will just put a few questions for this session. Explain isomerism with the energy level diagram. Explain the condition in which internal conversion can take place. How is nuclear reaction different from chemical reaction? Outline the conservation laws valid for nuclear reactions. So, we shall continue later. Thank you.